Section 5.4, we've been looking at, we've looked at dealing with the natural logarithm and integrating it and differentiating it. In this section, I just want to talk a little bit about its inverse function, e to the x. So we're going to look at a few of the properties of the natural exponential function, differentiate and integrate it. Yay! So we defined e by this number that if I take the natural log of e, I get 1. And using the fact that our properties of logarithms, if we took the log of x to the n is n times the log of x. Oh, that's an error there. I should fix that. I'll do it this way here. I'll cheat. I'll fix it on the slideshow, guys. Oops. I went ahead here. Go here, then go there. Now let's fix this. So that way the natural log of e to the x is x times the natural log of e, which is just x. So the natural log and e to the x are inverse functions. They undo one another. And that's one of the things we like about e, the natural exponential function. So we basically denote that the inverse function f inverse of x is e to the x, yada yada. So if y equals e to the x only if x equals the natural log of y. We're just trying to define this in terms of inverses. But again, they're inverses, so the natural log of e to the x equals x, and e raised to the natural log of x equals x. And we use that idea for solving equations, because when we solve equations, we use inverse operations or inverse functions. So you've probably seen problems like this back in pre-calculus. We used a trick, or the way I often teach this in pre-calculus is just using switch it to the other form, switch it from exponential form to logarithmic form. But I want you to do this using those inverse properties we just showed, just to kind of get a feel for that. So use the inverse properties to solve these. Okay, what do I mean by that? Here I have e to a power. I'm going to use the inverse property. So I'm going to take the natural log of both sides. The natural log of 7 equals the natural log of e to the x plus 1. Well, the natural log of 7 is just a number. I can plug it in and get that if I really need it. But here, the natural log of e to the power cancel each other out, so we just get the power, x plus 1. So we're going to get x equals the natural log of 7 minus 1. And that's using that inverse property to do this. Now on that one, let's get rid of my little blue X. Erase. Here I have a natural log. The inverse of natural log is the exponential function. So I'm going to plug both of these into the exponential function. So I'm going to say e raised to the natural log of 2x minus 3 equals e raised to the 5th power. Again, e raised to the natural log, they cancel each other out. They're inverse functions. So I end up with 2x minus 3 equals e to the 5th. And I really could find that number if I wanted to, but it's irrational and I don't want to. So I get 2x equals 3 plus e to the 5th. So x equals 3 plus e to the 5th, all divided by 2. So that's the way we can take advantage of this inverse property in order to help us solve these equations. So, getting back to what E is, and I know, we spent a lot of time in E before, Algebra 2, pre-calculus, yada, yada, yada. But, again, kind of looking at it from our new definitions ways here. Here's our graph. It's a nice exponential graph here. The domain is all real numbers. You can take e to any power, but the range is 0 to infinity. It never gets down to 0. That's an asymptote. It goes on to infinity. You will never get a negative answer from e to a power. It's continuous, increasing 1 to 1, concave upwards. And again, here's our end behaviors. As we go to negative infinity, we go to 0. Positive infinity, we go to infinity. And our properties with exponents is, if we take e to a power times e to a power, we can just add the powers. If we divide it, we can subtract the powers. Again, properties of exponents. The same things that work for all exponents work for the e stuff. So, what if we take the derivative of this? We're going to start off with, instead of, I don't know where to go with e to the x, so I'm going to start with this one. I know the natural log of e to the x equals x. That's a definition I can start with. I can do the derivative of both sides because I know how to take the derivative of a natural log. So the derivative of natural log is going to be 1 over e to the x times the derivative of e to the x. Well, I don't know what the derivative of e to the x is, but I can do that. The derivative of x is just 1. But now if we multiply both sides by e to the x, we get the derivative of e to the x equals e to the x. Isn't that cool? If you look at the function, that e to the x function, at any point, the slope of the tangent line of that function, y equals e to the x, at any point is the value of the function at that point. Is that not awesome? Derivative of e to the x equals e to the x. Derivative of e to the u is e to the u times du dx. So, yeah, chain rule. Simple. Nicest things to find the derivative of is e to a power. So, going silly on you here. We're about the end of the class, so we can be silly in here. If you're familiar with the song, I'm My Own Grandpa. I believe it was written by Ray Stevens, but again, if you have my slideshow, you can watch this. This is when the Muppets did it, because I like the Muppets. I'll put the link to this video in my in the description if you don't have my slideshow and you want to watch the Muppets sing I'm My Own Grandpa. Enjoy! Calculus should be fun, right? So let's try some examples with this. Give these a try, and then I'll work them out with you. Ya-da-da-da-da. First one is pretty much straightforward. Definition of e to the u is e to the u times u prime. So we're just going to get e to the 2x minus 1 times the derivative of 2x minus 1. It's just 2e to the 2x minus 1. Sweet. We take d, the derivative of e to the negative 3 over x. We're going to say, well, that's going to be e to the negative 3 over x. And then look at, if the derivative of negative 3x to the negative 1, let's make that, is negative 3 times negative 1 times x to the negative 2. So that's 3 over x squared. So that's going to be 3e to the negative 3 over x divided by x squared. Last two, I'm going to move on to the other different page to do it, give myself a little bit more room. So we'll come here, get off yellow, because yellow, well, oh, I'm on red, that's good enough. When we had the derivative of x squared e to the x, here we need the product rule. So the derivative of x squared times e to the x plus x squared times the derivative of e to the x is e to the x. So we have a common x in here. We have a common e to the x. And we're left with 2 plus x. Last one. Derivative of e to the 3x over e to the x plus 1. It's quotient rule time. I mean, we can't really simplify this anyway because that's not a monomial. There's no really nice thing to do with this. So we'll take the denominator times the derivative of the numerator, which is going to be e to the 3x, times the derivative of 3x. We subtract the numerator times the derivative of the denominator, so that's just going to be e to the x divided by e to the x plus 1 squared. And then say, okay, e to the 3x times e to the x is going to be e to the 4x. And we got a 3 in front of that. We have plus 3e to the 3x minus e to the 4x over e to the x plus 1 squared is going to be 2e to the 3x plus 3e to the 4, 2e to the 4x plus 3e to the 3x over e to the x plus 1 squared. And we can take out a common e to the 3x. So that would give me 2e to the x plus 1 times e to the 3x over e to the x plus 1 squared. Huzzah! Okay, not too bad working with derivatives with e to the x. So, for integrals, no big surprise. The integral of e to the x dx is e to the x plus c. The integral of e to the u du is e to the u plus c. So it's pretty much, yeah, e is nice. So we're going to work a couple examples like that. These I have worked out so you don't have to read my scrawling. So if I start off with e to the 3x plus 1 dx, instead of doing the u substitution there, I did the multiply divide by 3 so that I have e to the 3x plus 1 on 3 dx there. You know, that's again, looking at that pattern recognition version, we did that. So that's actually 1/3 e to the u du. So that's 1/3 e to the u plus c. So that's e to the 3x plus 1 over 3. He is nice to work with. We do something a little nastier here. So first thing, I regroup this. I pulled this x to go with the dx because I know the derivative of a negative x squared is going to have an x. It's going to be x. So I need an x dx when I'm dealing with this derivative. I have a constant in there, but I'll worry about the constant later. So if I make u negative x squared, then du is negative 2x dx, or x dx is a negative du over 2. So you see, that's why we did that regrouping there. I'm looking ahead. We saw what was coming. So I substitute that in, 5e to the u times a negative du over 2. Take out my constant. Negative 5 halves the integral of u du is negative 5 halves e to the u plus c. Then I substitute back in, and there we go. Now, that's about where we're going to get with on here. If I had more time, I'd go into, we've looked at natural log and we've looked at e to the x. These are really nice when we do integration and differentiation. However, if we do other logs and we do other bases, it's not that nice. So that's where we use a change of base formula. That's why if we can take something that's written, say, 5 to the x power and rewrite that as e to a power, then we can do all our cool e stuff. If we can change our log base whatever to log base e, then we can do all of our natural log things. It's kind of like when we did calculus, I said always use radians. If you're doing integrals and derivatives, you always want, and you have logarithms or exponentials, get them into e, get them into the natural base, either a natural log or a natural exponent, and then it works out really nice. Otherwise, it's a big headache. So that's kind of some of what we do if we had more time, but I don't have that time with you. So enjoy.